Hi guys. So section 7.6 is kind of like a summary section of our integration techniques. So there's really nothing new presented in this section. It's just a matter of we need to get good at realizing what to do in each type of problem. So that's what I'll really be stressing. I'm going to go in and look through some of my homework solutions in this section and see if you can follow along with me and follow the logic that I talk about in these problems. For the first one here, I have the integral of dx over x squared on the square root of 4 minus x squared. As soon as I see the inside of that square root is in the format of a squared minus x squared, I'm thinking, well, this is in the format of the section 7.3 problems where we had to do trigonometric substitution. So as soon as I notice that a squared minus x squared, trig substitution, in this format you're always going to let x equal a sine theta. Well, a is going to be 2 if a squared is 4. So I'll let x equal 2 sine theta. And now if x is equal to that, then dx would be 2 cosine of theta d theta. Now I can go into the problem and say, well, 4 minus x squared would be 4 minus 4 sine squared theta. And I know that that's going to be 4 times 1 minus sine squared, which is cosine squared. And then I know that that is inside of a square root, so when I plug it back into my problem, that's going to become 2 cosine theta right there. Notice I had a dx in the numerator, that was the 2 cosine theta d theta. My denominator is x squared, which we know is just going to become our 4 sine squared theta, and then times dx, that's our 2 cosine theta here. So now I can say, all right, clearly the 2 cosine thetas cancel out really nicely, and I would have a factor of 1/4 brought out in front, and I have a sine squared left in the denominator. I went ahead and said, well, sine squared in the denominator is the same thing as cosecant squared. Then I'm remembering from calculus 1, I can say, well, the derivative of cotangent is negative cosecant squared, so the derivative of positive cosecant squared is a negative cotangent, including the coefficient out in front of the integral. So I get negative 1/4 cotangent of theta plus the constant of integration. Now I need to go back in and fill in what the cotangent of theta in this problem is. And I know cotangent is the ratio of adjacent over opposite, so I'll draw a trig triangle here with this original trig substitution. I know that x over 2 would equal the sine of theta. Please notice within a right triangle, the side opposite theta had to be x, the hypotenuse had to be 2, because sine is opposite over hypotenuse. And then clearly our adjacent side has to be the square root of the hypotenuse squared minus the other leg squared. And again, whatever's in your problem must pop up in your trig triangle, and it did. So now when I go back to my problem here, I'll have negative 1 over 4 times the adjacent over the opposite side, the root of 4 minus x squared over x, plus your constant of integration. There's really not a lot you can do to simplify that. I just went ahead and put my negative 1/4 in the same fraction with the root and the x. Now, the next one I'm going to look at, number 13 in the homework. It asks me to integrate the cosine squared of 4x. What I'm wanting you to remember here, this is a trigonometric identity. The cosine squared x is equal to 1/2 times the group 1 plus the cosine of twice the angle. It's precisely what I did here. So anytime I have the cosine squared of any angle, I can say that's equal to 1/2 times the group 1 plus the cosine of twice the angle. Now, this is easy to integrate. I can integrate 1 and get an x. I can integrate the cosine of 8x, and I get the sine of 8x divided by the derivative of the angle, 8. That's where that 1 over 8 came from out in front. Of course, you could distribute through the 1/2 if you wanted to. You don't have to. And then plus your constant of integration. And again, the trig identity I used from this step to this step, right here. Next one I want to look at, actually I'll skip 15 and look at 17 with you. You can tell I had the whiteout portion of 17 here. But now in this one, you have the integral of dx over x squared plus 9. So now keep in mind, so far we've had a problem with a trig substitution where you had to recognize a squared minus x squared. This one had trig, but it's not trigonometric substitution. You're just simplifying an integral that already originally had trigonometry in it. And when I simplified it, it became pretty easy to integrate. This one goes back to another trig substitution example, and instantly you have to recognize that, because on the inside of this group you clearly have an x squared plus a squared. That's one of the dead giveaways for trigonometric substitution. Anytime you have that, you let x equal a tangent theta. So in this case, it's going to be 3 tangent theta. So then dx, the derivative of tangent, is secant squared. So I can say, okay, secant squared theta d theta. I went up here and thought about what that x squared plus 9 is going to be. I know that that's going to be 9 tangent squared theta plus 9. You factor a 9 out of that group and you would have tangent squared theta plus 1, which is secant squared theta. So the part inside of that group squared is 9 secant squared theta. Now you'll notice I went ahead and put that inside the group squared in the denominator. My numerator is dx, which I already knew was right here. Now from this step to the next, what I've done is I said, well, that denominator is 9 squared, which is 81. 3 over 81 reduces down to 1/27. On the inside of this group, you'd also have secant to the 4th in the denominator. So secant squared over secant to the 4th would be 1 over secant squared. And you'll see I wrote it as cosine squared. We're going to use that same reduction trigonometric formula that I used in number 13 up here. The cosine squared theta is going to equal 1/2 times the group, 1 plus the cosine of twice the angle. That 1/2 factored to the outside, which is why the 1/27 became 1 over 54. Now, whenever you're integrating this, the integral of 1 is just going to be theta. The integral of theta with respect to theta is going to be the cosine of 2 theta divided by 2. It's the reverse chain rule there. Of course, plus the constant of integration. I can't leave that second term inside this group to be the sine of 2 theta because I can't get it back in terms of x. So I use yet another trigonometric identity that says that the sine of 2 theta is equal to 2 sine theta cosine theta. And then I can say this 2 is going to cancel out the 1/2 in front, and I would just get this right here, 1 over 54 times the group theta plus sine theta cosine theta plus c. So now I'll have 1/54 times theta. Well, theta, we already know in this problem that x over 3 is equal to the tangent of theta because of our original trig substitution. So when I go in and I try to solve for theta, you would just say, well, it's going to be the inverse tangent of x over 3. That's where the first term comes from there. My second term comes from the sine and the cosine. If you notice your trig triangle from the setup of that tangent theta equals x over 3, so we knew opposite side had to be x, we knew adjacent side had to be 3, which meant your hypotenuse had to be the square root of x squared plus 9. And again, the expression from the original problem has to pop up inside your trig triangle, and it did. Now I can say, well, the sine of theta is just opposite over hypotenuse, x over the root. The cosine of theta is the adjacent over the hypotenuse, the 3 over the root. Then I have plus my constant integration. Last step is just simplifying. We know the 1/54 is going to be multiplied by the inverse tangent of x over 3. In this second group, what I did is I said 3 will go into 54 18 times, and I'll have the 3 cancels out. I'll still have an x in the numerator and a factor of 18 times x squared plus 9 to the first power in the denominator, plus your constant of integration. Now, that one's a pretty cool problem. If I look at another page here, the next problem, and I'm trying to specifically choose problems out of my book homework assignment that would be reflected in the online assignment. So if you have one like number 19 where you have an integral problem in terms of tangent and secant, you can say, this takes me back to section 7.2 where I was simplifying trigonometric expressions. I know anytime you have an odd power of sine, cosine, tangent, or cotangent, you're going to want to always break all but one power of it in terms of another trig function. So I can say, due to the Pythagorean identity that secant squared x minus 1 is equal to tangent squared x, I can say tangent to the fourth is equal to tangent squared, same thing as secant squared minus 1, quantity squared, times the remaining factor of tangent x. Now notice what I did with this. I brought that secant squared x minus 1 down, times the secant of x, times that lingering factor of tangent x that I did not account for here intentionally. And then you say, well, okay, this is perfect, because all I have to do now is let u equal the secant of x, and if I do, the derivative of u would be secant x tangent x. So all of this cancels out with my derivative, and I can say, okay, so the part that I have inside the group, it's going to be u squared minus 1 quantity squared. Everything else is du. At that point from here to here, I go ahead and I square out that group. U squared minus 1 is going to be u squared minus 1 times u squared minus 1, or u to the fourth minus 2u squared plus 1. You integrate this expression term by term. This one becomes u to the fifth over 5 minus 2u to the third over 3. And then the last one plus u to the first. Of course, plus your constant of integration. Once you have your answer in terms of u, you just substitute. We know that u is equal to the secant of x, so we get secant to the fifth x over 5 minus 2/3 secant cubed x plus the secant of x plus c. So now we've had a couple of problems with trigonometric substitution, and we've had a couple of problems dealing with the integration where we had a trig function in there in the beginning. 21, I want to look at it as well. It'll be our first problem in which you're supposed to recognize integration by parts in the first step. It shouldn't be hard at all to recognize, because integration by parts is kind of a dead giveaway the instant you have a natural log inside of your function. I would say 95% of the time your function includes, your integral includes a natural log, you'll be using integration by parts. So if I have the natural log of x to the fourth plus 1 with respect to x being integrated, I'll say, okay, let u equal, remember, u is always equal to liate. The very foremost thing to let u equal to is the logarithmic function. So I let u equal the logarithmic function. dv has to be the only other thing in there, which is dx. So now I differentiate u. Derivative of any logarithm is 1 over what's inside the logarithm times the derivative of what's inside the logarithm with respect to x. The integral of 1 with respect to x is just x. So now I come down here and I say, well, my original integrand then is equal to u times v. So I said x times the natural log of x to the fourth minus 1. Now keep in mind, that part's done. Minus the integral of v du. Well, v times du, that's going to give me x times 4x cubed is 4x to the fourth. I went ahead and factored that 4 out front. And then we have x to the fourth minus 1 in the denominator with respect to x. At this point, as soon as I saw I had a rational function on the inside and the degree of the numerator and denominator was the same, boom, I did long division. So I divided that denominator into the numerator. I know x to the fourth only goes into x to the fourth one time. But then 1 times x to the fourth minus 1 gives me x to the fourth minus 1. I subtract that group out. Clearly the x to the fourths cancel out, but I'm going to be left with a positive 1. That actually really helps now, because I can say, well, then this last integral, I'll keep my minus 4 in front of the entire group and say, well, it's just the integral of 1, this part that divided evenly with respect to x, plus any remainder that you get still has to be inside of an integral divided by x to the fourth minus 1. So this part right here, super easy. The integral of 1 with respect to x is just x. I keep the minus 4 in front of it. And notice I just brought down the first term. This last one, though, it's going to be a little bit more problematic, because you have a denominator of x to the fourth minus 1, which is a difference of 2 squares. It would factor to be x squared plus 1 times x squared minus 1. But then that second factor of x squared minus 1 further factors to x plus 1, x minus 1. So this is the fully factored final form of that denominator. And I can say, well, now once I see it is factored, I'm going to have to use partial fractions to simplify out this last one. And it's critical that you understand that. Anytime you have factors in the denominator, you're most likely always going to use partial fractions. Over any quadratic factor, I need a linear, so the first term I have ax plus b over x squared plus 1. The two linear factors just have constant numerators, so I'll have plus c over x plus 1 plus d over x minus 1. Now I need to try to solve for a, b, c, and d. From this step to this step, all I did was I took the entire equation and I multiplied by x squared plus 1, x plus 1, and x minus 1. When I do that on the left-hand side, I just get a 1. When I do that on the right-hand side, I'll get ax plus b times x plus 1 times x minus 1 here. I'll get the c, it's going to be times everything except the x plus 1, so you have the quadratic factor of x squared plus 1 and the linear factor of x. When I go to the d term, it's going to cancel out the x minus 1, but you're going to have d times x squared and x plus 1. So now, in order to solve for a variable, you look at your denominators. If you can force any of the denominators to be 0, you'll be able to solve for a variable. This one can't be 0. This one can, though, and so can this one. You'll see first thing I did is I had that last one equal 0 by letting x equal 1. If x equals 1, your left-hand side, it's still 1. It doesn't have an x term. If x is equal to 1 on the right, you can see your a and b would cancel out because they'll be multiplied by 0. C will cancel out since it's multiplied by 0. But you're going to have d times 1 plus 1 times 1 plus 1. That's where this comes from. I have 4d is equal to 1. So then I know, well, if 4d is equal to 1, then d is going to equal 1/4. Now, similarly, I went ahead and plugged in a -1, and when I did that, I can see that the ax plus b terms will cancel, and the d term will cancel because they both have a factor of x plus 1. However, you can plug 1 in beside c, and it's not going to cancel out. You'll get -1 squared plus 1. That's going to be a 2. And then I'll get -1 minus 1. That's a -2. So I can see that this variable is going to be multiplied by -4. I'll have -4c is 1. Thus, c is -1/4. Now, once I get my answers for c and d, it makes it more easy to find your answers for a and b. So in order to do a, what I did is I said, think of the x cubes in this problem. And you might say, well, there is no x cubed on the left-hand side. Well, that tells me the coefficient of x cubed is supposed to be 0. The only way I would get x cubed terms on the right is for an a x cubed, and then I can say c would be the coefficient of an x cubed, c times x squared times x, and d would equal the coefficient of an x cubed, d times x squared times x. So I know a plus c plus d has to equal the coefficient of x cubed, which is 0. And then I can say, well, I'm solving for a. I know that c and d are just the opposites of one another, so they immediately cancel each other out. So I'll get a is equal to 0 as well. Now, in order to find the remaining term, I said, look at the constants. On the left-hand side, your constant is 1. On the right-hand side, the way I can get a constant, I could multiply b through this group. I would get b times 1 times -1, so negative b is a constant. And I could say c times 1 times -1, negative c is a constant. And then d times 1 is also a constant. So I can say negative b minus c plus d, it would be my constant term on the right. I know that that's going to give me, well, on the left-hand side, the coefficient constant 1 is already in existence. I know I'm trying to solve for b. I would say negative b minus c. So that's going to be plus 1/4. And then plus d plus 1/4. So I get negative b plus 1/2 is equal to 1. That's going to give me negative b is 1/2. Thus, b is equal to -1/2. I have to get that. So now, the point of this problem, we were trying to take, and again, right now I'm just working with that last partial fraction term that the integration by parts did not handle. So I already know the first two terms. I'm working on this term. So I can say, well, then that last term there is going to equal, I know I'm breaking it up into ax plus b, and I said, well, a is 0, I know b is negative 1/2, so instead of putting a negative 1/2 over x squared plus 1, I went ahead and factored the negative 1/2 to the front. And then the plus c over x plus 1, I know c was minus 1/4, I brought the minus 1/4 out in front, times 1 over x plus 1. My last term would be d over x minus 1, so I know, well, in this case d was 1/4, so I put plus 1/4 on the integral of 1 over x minus 1. Now, anytime you have fractions where the derivative of the denominator is in the numerator, these are nice logarithms. So you're going to have minus 1/4 natural log of x plus 1, plus 1/4 natural log of x minus 1, both inside absolute values there. The first one is a little more challenging, but you just say, oh, that's by formula, 1 over x squared plus 1, that is your inverse tangent of x, and so I'll keep the negative 1/2 out in front. Now, I know what the answer to all that last integral is. Now it's just a matter of taking my answer, the first two terms, x natural log of x to the 4th minus 1, minus 4x, and then I need to remember I need to distribute a negative 4 times every single one of these terms because they were all inside of an integral multiplying a negative 4. So you'll see that's why I have plus 2 inverse tangent of x, and then it would be plus this natural log minus this natural log when I multiply by the negative 4 term. And so I'll just say, well, I've condensed them down to 1. It's going to be plus the natural log of x plus 1 divided by x minus 1. It's not wrong to keep them out as separate logarithms. I just chose to condense here. And then, of course, we have plus our constant of integration. Now, another one that I want to look at with you. That one had a nice combination of your integration by parts and the partial fractions in it. This one, again, it's going to have a nice combination of some methods in here. If I look at 25 with you, you have the integral of x plus 1 with respect to x over x squared plus 4x plus 8 quantity squared. So I know automatically that the derivative of what's inside of this denominator, it's almost in that numerator. Notice that's why I tried right here. I said, if I let u equal x to the 4th plus 4x plus 8, its derivative would be 2x plus 4. And I know 2x plus 4 is the same thing as 2 times x plus 2. Well, my numerator was x plus 1. That's very close to what I needed. So here's what I did in this problem. I said, well, if I took that numerator and I went ahead and I needed to get a 2x plus 4 up there, then I can say, well, I could multiply what I have in the numerator by 2 and then divide the outside by 1/2. Those are equal yet opposite operations, so this is still the same thing as what I had. But even if I multiply that by 2, I would still just get 2x plus 2. I need a 2x plus 4 up there. So I went ahead and I said, well, let's add 2 up there just to force this in there. Now, if I add 2 to the numerator, then I need to subtract 2 in the numerator. It's better to do that in a separate integral. So you'll see I have minus 1/2 times this integral. You have plus 1/2 times the integral with a 2 inside of there. So now you have to have minus 1/2 the integral with a 2 inside of there to make up for what you did right here. Why did I do this? Because I needed to force the substitution of the problem. Now, in order to do that, and I need to put a dx here to make this one technically correct. I'll fix that. So in order to do that, I had to subtract it out. Now this first one, I'm looking at it and saying, well, if I let u equal all of that, then du is up in my numerator, the 2x plus 4 times dx. So my numerator becomes I should have said du. My numerator, all of this times dx becomes du. And then I can say, well, this is just going to be 1/2 the integral of du over u squared. We know that that's going to be equal to u to the -2. Whenever you integrate u to the -2, you get u to the -1 over -1. That's going to make this minus 1/2, and down in the denominator with the 2, you're going to have a u to the first. That's the u to the -1 in the denominator as u to the first. So the first integral is done. Now I need to work with the second integral, and what I've done from this step to this step is I just said, well, if you have a 2 on the inside and a 1/2 on the outside, you have to cancel those. And I can say, well, it's just minus 1 on the integral of 1 dx over this group squared. So I have this. Now when I'm thinking of what do I do in order to get to my answer, well, I know that this is probably some type of a trigonometric substitution problem, but it's not in the format where I can deal with it, because trig substitution needs to have x squared plus a squared minus x squared, or a squared minus x squared plus a squared, or x squared minus a squared. That's your three different forms. I'll get it right. Now, when I'm looking at this, I can say, well, that's none of those forms. So I need to take that group, the x squared plus 4x plus 8, and notice I wanted a perfect square trinomial. I knew that the third term in there had to be half of 4 squared, so I wanted a 4 in there. So that remaining part of that 8, I just pushed to the outside. I have x squared plus 4x plus 4 plus 4. Now, the x squared plus 4x plus 4 could be written as the group x plus 2 quantity squared, and then I have a plus 4. At this point, I'm wanting you to recognize, okay, you have a variable squared plus a constant squared, so it's in a similar format to what we see x squared plus a squared. So instead of using another substitution that would be completely unnecessary, I'm going ahead and saying, well, your variable in this case is whatever x plus 2 is. What do we need x plus 2 to equal? We need it to equal a tangent theta. So I say, well, a in this case is 2. We'll have 2 tangent theta dx, and again, remember the derivative of x plus 2, same thing as the derivative of x. It's dx. Derivative of any constant is 0. I move to the right hand side, derivative of tangent is secant squared. I get 2 secant squared theta, d theta. So then that group that's in the denominator, that x plus 2 squared plus 4, we know that that's going to be x plus 2 is 2 tangent theta, so this is going to be 4 tangent squared theta plus 4. Factor 4 out, you get tangent squared theta plus 1, which is secant squared theta. So now I know that, and again, remember, this is the part inside of that group squared. So the part inside of the group squared is 4 secant squared theta. So I can say, okay, my integral answer was, and this is all that first part, -1 over 2u becomes -1 over 2 times this group right there. That's where that answer came from. And then now minus this integral. Well, the dx in the numerator we've already shown is 2 secant squared theta d theta. The denominator is going to be 4 secant squared theta quantity squared, which is why I put 16 secant to the 4th theta down there. And then once we do that, you'll have your minus, I can factor the 2 over 16 out as 1/8, and you'd have a secant squared in your denominator, and you can say, that's that familiar answer that pops up a lot. Secant squared in the denominator means a cosine squared in the numerator, and then you can use your trigonometric power reduction formula. Cosine squared is 1/2 times 1 plus cosine of 2 theta. Then we can integrate and then use our double angle formula to say that the sine of 2 theta is 2 sine theta cosine theta. That's where this comes from. The 2 sine theta cosine theta, the factor of 2 cancels out with the 1/2. So now, and again, remember, we're just working that cosine squared theta at this point. So I integrate all of that. I'll get 1/2 times theta plus sine theta cosine theta. I needed to go to my trig triangle. And I can say in this trig triangle, what we've done here is we said, well, if x plus 2 is equal to 2 tangent theta, then the tangent of theta is equal to x plus 2 divided by 2. So then I can say, well, all right, in my trig triangle here, the side opposite theta had to be x plus 2. The side adjacent to theta had to be 2. So your hypotenuse had to be the square root of this side squared plus this side squared. So I said x plus 2 quantity squared would give me x squared plus 4x plus 4. It's right here. And then we're adding a 2 squared to that plus 4. It just takes me back to this x squared plus 4x plus 8. But now, of course, it's all inside of a square root for the hypotenuse of that right triangle. Now I can go in and say, well, okay, when I try to simplify this, the theta, that's just going to be the inverse tangent of x plus 2 over 2. Plus, I have sine theta, cosine theta. Sine theta, opposite over hypotenuse. Cosine theta, adjacent over hypotenuse. I put those two in, plus your constant of integration. So now, again, I'm pulling all of this integral together. Remember, we already had this answer up here, negative 1 over 2 times the group x squared plus 4x plus 8. Now when I tally that together with what I have here, this is just the integral of the cosine squared of theta is this. We have to multiply all of that by a minus 1 over 8. So you'll see that's where the minus 1 over 16 inverse tangent of x plus 2 over 2 comes from. And again, the second term would be minus 1 over 8 times 1/2. That'd be minus 1/16. But now that 1/16, I canceled it with a factor of 2 there. And you'll see that's why I have minus 1/8. I have a factor of 8 in the denominator times these two roots. Gives me that group to the first power. And the 2 canceled out, but I still have a factor of x plus 2 in the numerator. And then plus my constant of integration. And then at that point, I can see that, hey, please notice I have the first and last term here where I could go ahead and collect a common denominator. I could say, all I would have to do is multiply the first one by 4 over 4, and I would have the same denominator as this last one. If I did, this would be negative 4 over 8 times that trinomial. So I have negative 4 minus x plus 2, so that's negative 4 minus x minus 2. That gives me negative x minus 6 over that combined common denominator of 8 times x squared plus 4x plus 8. Minus your 1/16 inverse tangent of x plus 2 over 2, plus your constant of integration. It's a gorgeous problem.